Okay, so we're going to now begin to look at the derivatives of the natural log and the natural exponential function in this video. Okay, let's begin our look at the derivative of the natural log of x. In a previous video, we saw graphically that the derivative was 1 over x in the first quadrant. Okay, so now we're going to put a little more analytical approach to that. Let's bring in the derivative operator on both sides of this equation. Okay, and working down, we now know this notation is the rate of change of y with respect to x, which of course we know that is y prime as well, so let's not forget that, equals, and we saw that the derivative here is going to be 1 over x, with x being greater than 0. All right, well that would be nice and lovely if we could all day long say that that's the derivative of the natural log function, but unfortunately they're probably going to give us a little more complicated, or a composite if you will, natural log function. Okay. All right, so let's take a look at what that might look like. Okay, let's say we do have a natural log function. Our outside function is the natural log, and that inside function is not just, say, simply x, that it's perhaps u, where u is another function of x. So what could that look like? Well, that just simply could mean that y is equal to the natural log of 2x, 8x, could be natural log of parentheses x squared plus 4, end parentheses. Okay, so we're looking at an inside function here. So the natural log is the outside function and u is the inside function. So we do know that our work with that composite function would involve the chain rule. So we're going to bring in the derivative operator. Ooh, that needs to be the natural log. See, oh no. No, we don't want to do that. And we certainly don't want to do that. Okay. All right, so applying our differentiation rules, we have dy dx equals, okay, the derivative here. So when we study this function right here, we're looking at it and we're, okay, well, the outside function is the natural log. It's not a power function. It's not the power rule. Okay, so we have to make a connection in our brain. The natural log function's derivative is 1 over x. It's 1 over x. So here we're going, all right, the derivative of natural log is 1 over not x, but u. So we're building a fraction, putting 1 on top with our u in the denominator, just like we did here. We built a fraction, we put x in the denominator with a 1 on top. Okay, well, we're not done yet. That's the outside function, 1 over x, if you will. Okay, so chain rule has us find the derivative of the outside function, which is the creation of this fraction, times the derivative of the inside function. Well, the inside function is just u, whatever that might be. Okay, so this derivative, using the chain rule, is just simply 1 over u times du dx. Some authors replace du dx with u prime, and they say that derivative is 1 over u times u prime. Some authors even yet stack it as a fraction and say, well, that's just going to be u prime over u. Okay, so the inside function making up the denominator in this fraction answer, and the derivative of that inside function being in the numerator. Okay, so these are the rules that we want to begin to memorize. Unfortunately, there are more. Okay, if we're dealing with a natural log function, we have to tap into these rules right here where we create a fraction with 1 in the numerator and the inside function in the denominator. Okay. All right, so let's look at some examples. Okay, let's say we want to find the derivative of the natural log of parentheses 2x. Now, something that we could do is we could use properties of logs here. If you remember in an earlier video, this would be equal to the natural log of 2 plus the natural log of x. And if you did use properties, that'd be fine. Okay, then we'd have to actually differentiate. So, but in this case, I don't know if properties would be real helpful. It might be good to look at both ways. So let's go ahead and do that, I guess. Let's look at the properties here. So that would be the natural log of 2 plus the natural log of x. Product property. Okay, so that's what y is equal to. Now, again, my objective is to find the derivative. So let's come in and find the derivative of each of these terms. I don't know what natural log of 2 is unless I type it in on the calculator. But what I do know is that the derivative of a constant, that number, is just going to be 0. So then I move over to this term. What's the derivative of the natural log of x? Well, that's just simply 1 over x. So it's kind of interesting that if you put a coefficient here, what happens is your derivative is the same. So that would be if I use log properties, and then after I use log properties, differentiated using the correct differentiation rules. Okay. So let me come over here and call this 1a. Okay. Let me go back to that same example. Instead of using properties, this problem isn't too bad at all if you don't use properties to break it apart. Okay, so what if I didn't use properties and I jumped right into the derivative using the chain rule natural log derivative? All right, well, I want to identify this as my inside function, if you will, my u. So my outside function is natural log, so that derivative creates a fraction with u in the denominator, which is my inside left alone, times the derivative with respect to x of my u, my inside function. We all know that goes to 2, so in my next problem here, or my next line, I'm going to have 1 over 2x times 2. Well, I'm going to go ahead and put 2 on top. I'm going to simplify it, and I indeed get the same thing that I got here from a different approach. You know, when I compare these two approaches here, I don't think one's easier than the other, so properties, you know, maybe not have been real helpful. They will in a later problem. So let's look at some more examples of finding the derivatives of natural log functions. Okay. Okay, so my objective here is to find the derivative. One of the things I just kind of real quickly take note of is that if I'm dealing with a log function, I always try and think before I differentiate, would it be helpful to use some of the properties to simplify this, break it apart? No, I don't see that I can use any properties, so actually I just need to get right into the derivative. So bringing in the derivative operator, identifying this as my u, the derivative is 1 over u times the derivative with respect to x of my u. And I know some of you guys are looking at this going, oh, I can do this mentally. Do I have to show that step? No. But again, like I've said on previous videos, it's risky if you don't show this setup here. This derivative is 2x. Well, where does it belong? Well, it's going to probably go in the numerator here, so I can get right to the answer, okay, and get the derivative. You know, just take note of this derivative. The denominator is the inside function here, and the numerator is the derivative of the denominator, the inside function. Okay, let's come over here. Okay, let's look at y equals x natural log of x. As you study that equation, I'm hoping you're already thinking that, you know what, this looks like the product rule because I have a multiplier that's not constant. I have a variable multiplier times another variable function. So this is the product rule. So we have a new rule, but we have to be able to use it with chain rule, product rule, and previous rules. So first times the derivative of the second plus the second variable factor. Okay, remember this is f and g. Times the derivative of the first. Sometimes I use parentheses, sometimes not. So y prime equals derivative of the natural log is 1 over x. So that would be x times 1 over x. That'll simplify to 1. Again, this whole thing goes to 1 over x. So 1 over x times x over 1 simplifies to 1. Plus, this derivative goes to 1, so plus 1 times natural log of x. So product rule there. Okay, looking at this function right here, this example, again, like I said, I was trying to examine whether I can use any properties, log properties, to help me before I go into calculus and differentiate. No properties can be applied here. I'm studying this, and I'm going, the outside function here is now x cubed. The inside function is natural log. So it's a chain rule. So the outside function is a power function, so I'm going to use the power rule, bring the 3 in front, leave natural log x alone, drop the exponent to 2, but multiply by the derivative of the inside function. Taking note that the derivative of this function is 1 over x. This is a multiplication. So times 1 over x. I'm going to put the x in the denominator, and then this will all stay up here in the numerator. Again, like I've mentioned, that square could go on the natural log function here, but not on this x right here. Or you could write it in this alternate way form right here. Let's find the derivative of this natural log function right here. Well, I'm trying to avoid too much complication when I have to find the derivative. And if you think about this part of the problem right here, this angle, that's quantity x plus 1 to the 1/2 power. If I were to jump right into finding the derivative, that would go in the denominator of a fraction with 1 on top. That is 1 over this square root would. Then I'm going to have to multiply by the derivative of the square root of x plus 1. Properties, log properties, the reason we did log properties is to make these kinds of problems easier for us. So if you see that you can take advantage of log properties, no calculus, to rewrite something, it's going to make the differentiation a lot easier. Taking the square root off as a rational exponent, moving the 1/2 in front as a multiplier. Okay. I just removed the whole situation of a power of 1/2 and having to deal with that. This is just regular y. Now I'm going to jump into y prime. Constant multiplier stays in front. Focus your attention right here. Outside function is natural log. Immediately build a fraction. 1 over x plus 1 times the derivative of x plus 1. That derivative here is just 1. Final answer. I'm not going to distribute the 2. It's better to leave everything in factored form. That way you can see if anything cancels. Okay. And one more example of finding the derivative of a natural log function. Okay. It looks like we may have saved the best for last here. So. The cube root. Goodness. All right. Imagine, if you will, us having to find this derivative, this natural log derivative. This whole thing right here would be considered our u, our inside function. When we went to find the derivative, we'd have to put 1 over this ugly fraction times the derivative of that fraction. Here's where log properties, we're not going into y prime, we're going into log properties, are going to help us with our work. Okay, so let me go ahead and expand this. So it looks like in the numerator I have the natural log of x, I have a product, plus the natural log quantity x squared plus 1 squared, I'll come back and take care of that later, minus, now I'm going to the denominator and I've got the natural log. I need to rewrite this as a 1/3 exponent. The minus here means I'm in the denominator. I don't need a negative because of the properties of exponent allowing me to do this. I still can use another property here, the power property. Okay, and remember, I'm not reducing this. I'm not in calculus. I'm just moving and shifting that. Okay, now I'm ready to find the derivative of each term. So easy enough, 1/x plus, okay, we have a constant multiplier of 2 here, so 2 can be put over 1. I'm anticipating fractions, times, all right, we have a log function. Its derivative is 1/x² plus 1. And if you would allow me right here to multiply by the derivative of x² plus 1, that being 2x, and skipping the setup stage, going on to this term, minus 1/3 times 1/, the inside function, times the derivative of each of these terms, which is 6x². And here's a little cleanup, and we'll be finished. 1/x plus, looks like I would have 4x over quantity x² plus 1. It appears that this is going to be minus, should be a plus. Another fraction here. Appears that I can cancel 3 in here twice, so I think I have 2x² over 2x³ minus 1. Okay, so we've just practiced finding the derivatives of natural log functions, the parent function and a composite function.